Hello everyone, this is a sequel to my video Definition of Cross Product. In this video I would like to go over two important properties of cross product. The first property is about the meaning of the magnitude of a cross product. In the earlier video I introduced the definition of cross product as a formula that rises when we use Cramer's rule. As in the earlier video, if we put this in the context of a 3x3 matrix, we get a good answer to this question. The second property shown here is called the triple product, and it is an important formula for the geometry of physics. And in my course I use this formula for the curvature of a space curve and for Newton's universal law of gravitation. Before we move on to the details of this property, let me say a few things about this property 2 here. On the left hand side we have this B cross C, and because this itself is a cross product of two vectors, this left hand side is a vector that is perpendicular to A and the perpendicular to the cross product of B and C. Therefore this vector must be contained in the plane that is spanned by these two vectors in B and C, because all the vectors that is perpendicular to B cross C must be spanned by these two vectors B and C, and that's why the right hand side is of this shape. And we need to look at the detail to understand why the coefficients of a B and C looks exactly like that. Okay, let's look at the first property here. Let's recall this fundamental result from the linear algebra. If three vectors A, B, and C form a parallelepiped, shown in the figure here, the volume of this solid is equal to the determinant of this 3x3 matrix up to sign, and by the cofactor expansion and the definition of the cross product, we have this dot product version, as you can see on the right side of the equation. And it turns out that this dot version makes the connection to the property of our interest here. As in the figure, let B be the area of the base of the solid, then the volume is equal to the base times the height. And the height h is the scalar projection of vector C up to sign. And let's use this formula for the scalar projection to write this idea. So here it is. The scalar projection is this dot product over the magnitude of the vector that we're projecting onto. So the volume becomes this guy right here. So I was a bit slow with this editing video, so let me say that again. So the volume of this parallelepiped has become this guy, because it's base times height, and I'm substituting h with this scalar projection version. I forgot where I stopped. So here we get triple product version of the volume and the base times height version of this two volume. So if you solve for B here, then we arrive at this property that which is almost the first property we try to prove here. Now it takes just a simple trigonometry to finish off the proof of the first property. The area of the parallelogram is base times height, as you can see in this new figure appeared there, and the height is this length here, the length of that one, which is the magnitude of vector B, times the value of the sine, where the angle is the angle between these two vectors. So this concludes the proof of the first property. Now let's take a look at the second property here. First of all, if the vector B and C are scalar multiple to each other, in other words, if they're pointing in the same or perfectly opposite direction, the left hand side is going to be 0 vector, and substituting C with this k times B, the scalar multiple of B, and we get the right hand side 0 as well. So let's assume it is not that case, namely assume these two are linearly independent vectors. if B and C are linearly independent, then BC and the cross product B cross C form a basis of the space, and we may write an arbitrary vector A as a linear combination like this. Now let's apply the cross product to this version. So then the third term, as you apply this cross product of B cross C, then the third term has the cross product of the same vector, and it becomes 0. And we come to reduce the problem to the property of two vectors in B and C as follows. Now I'd like to claim here without proof that it is sufficient to prove the property for this case only, since it is relatively easy to use it to prove the general case with a vector A. Now let's focus on this case now and let the R be the product as shown here. So here I sketch the vector B and C here. So if we use the right hand rule to B cross C, it's pointing toward us. Now if we use the right hand rule again to the triple product and the vector C, excuse me, not the triple product, the vector C and the B cross C, which is pointing toward us, if we apply the right hand rule to that vector in that order, then the triple product comes back down to the plane, making a 90-degree angle with the vector C, and the direction of that vector is as shown in the figure. If the two vectors B and C are in different configuration, we can go to the other side of the plane, and then you can see we're back to the same configuration again. So here I sketch the both vectors so the both angles are counterclockwise oriented, but if theta is obtuse, then theta bar will be clockwise, being a negative angle. Nevertheless, for both cases, the sum of the two angles is a 90-degree. So this theta plus theta bar is going to be pi over 2 radian. So here's another picture. Let these vectors V and W be the projections of the vector B, as shown in the figure. Then by the projection formula, we get these two vectors. And so we see that V is a scalar multiple of C, because that vector V is parallel to C, and W is a scalar multiple of vector W there. Excuse me, the W is a scalar multiple of vector R. Another observation is that the sum of these two projections goes back to the vector B again. Here, let me remind you of this subtlety that if two vectors we're projecting onto are not perpendicular to each other, the sum is not equal to the original vector. You can easily verify these by sketching some examples on the paper. But here, our vector C and the triple product is perpendicular to each other, so this vector B and W is supposed to be the original vector B. So if we substitute with the dot version here and solve for R, we arrive here to this equation. Now let me explain this form we got here, I'm pointing, is already very close to the form we want to prove, which is in this equation, the triple product being this linear combination of B and C. So far we have proved this equation about R, which is the triple product, and this one in the red box is the result we wanted to prove. So this factor here is, if this factor here is a C dot C, then the denominator here cancels and it is multiplied to the vector B part, and we exactly get this statement we want to prove. So what we want is this factor outside in this first line. We want to show this is equal to the C dot C as I pointed here. So Let's prove this result, that the quotient of these two dot products being equal to this dot product, C dot C. Let's first unfold the magnitude of the vector R, which was the triple product. Sorry, I think I was explaining a wrong part. Let me go back to this part here. So this is the denominator of the left-hand side of the equation we want to prove, R dot B. And this is typical thing that the dot product is a product of the magnitudes times the cosine of the angle between those two. So R here is the triple product, and the other vector is B. Therefore, the angle in between here, is shown in the figure here, is a theta bar. Since theta plus theta bar is a pi over 2, we can write it as a sine theta. It's shown in this equation here. But the numerator of the left-hand side is R dot R, so that is the same as absolute value of R, the magnitude of R squared. So since we have one copy of magnitude of R both in the numerator and the denominator, they cancel, and it makes the left-hand side of the equation like this. Now with that magnitude of R in the numerator, we're going to unfold that magnitude of R in the numerator. This is shown in the equation. So here we have two vectors B and C, and C is perpendicular to B cross C, since it is the property of the cross product. So the angle between C and the B cross C must be 90 degrees. Let's recall the property 1, which is the magnitude of this. Let me repeat that again. The magnitude of this part I'm pointing here is the product of magnitudes times the sine value, which is supposed to be here, but because the angle is 90 degrees, the sine 90 degrees is 1, so that's why you don't see the sine part in the middle equation there. So if we substitute this result at magnitude of R to here, you can see magnitude of B cancels and sine theta cancels, and we're left with the square of the magnitude of C, which is equal to C dot C. So that concludes the proof of this statement I'm pointing there, and from the first line, that in turn implies that this particular triple product here is expanded as a linear combination in this form. And using this single result, you can get to the very general case just using the linearity of the general property itself. Thank you for watching the video.